Okay, dear students, I'm back due to internet connectivity. We have interruptions in our lecture, but we are uh, we are able to cope with them. Okay, so I was telling you that this knot of the permanent magnet is this power magnet is moving towards left. It's approaching this right side of this solenoid, and the galvanometer in this solenoid shows deflection to the right, and it shows that the current is flowing from A to B. And due to this induced current in this solenoid, when the current flows through the solenoid, electromagnetic electromagnet is formed on the solenoid, and that electromagnet will have a north pole here. On this right side, it will have a north pole here. And why it will have the north pole here? The reason is that it will try to oppose this approaching north pole. To stop the motion of this approaching north pole, the right side of this solenoid, it will become a north pole. I hope that you have understood this. And suppose, for example, suppose that we have, for example, when this north pole approaches the solenoid, the current induced in the solenoid its direction will be in such a way that the right side of this solenoid will have a north pole, and the reason is it's trying to oppose that approaching north pole. That's the Lenz's law, that the direction of the induced EMF is in such a way that it opposes the cause which is inducing it. I hope that you have understood this story. And let's go to the next slide. And so here we go. Here we have, uh, so when the north pole of the bar magnet was moved towards the solenoid, the galvanometer needle was deflected momentarily to one side. This shows that an EMF was induced in the coil and a current flowed through the galvanometer. The induced current produced an north pole at the end of the solenoid to repel the north pole of the bar magnet moving towards it. I hope that you have understood. And let's move. This slide is explaining in proper academic language the previous slide, that when a north pole of a bar magnet approaches the right side of the solenoid, EMF is induced in that solenoid, and due to that induced EMF, the electromagnetic field is produced around that solenoid, and that electromagnet will have a north pole on the right side of the solenoid to oppose the approaching north. Okay, here we have the second step, uh, and in that second step, you see what is happening here. We have a north pole, and that north pole has entered the solenoid, and now I have stopped moving the bar magnet. The bar magnet is stationary. It is no more moving. It is at rest. So you see the magnetic lines of that bar magnet are still passing through this solenoid. The magnetic flux of this bar magnet is still passing through this solenoid. But that magnetic flux is now not changing because the bar magnet is not moving. So you see, when the this bar magnet, it stops moving, it becomes stationary, the galvanometer shows no deflection. When it shows no deflection, it means there is no current induced in the solenoid. So from here we conclude that when the bar magnet is at rest, when the magnetic flux of the bar magnet is not changing, the magnetic flux which is passing through the solenoid, it is not changing. There is no EMF induced in the solenoid. So that's why the galvanometer is showing no deflection. Its pointer is at its zero position. So no EMF is induced if the bar magnet is not moving relative to the solenoid. Okay, so here you see we have a bar magnet, and this bar magnet, its north pole is facing the right side of the solenoid, and now this this bar magnet is withdrawing. It's moving away from the solenoid. It's moving away from the right side of the solenoid. This north pole of the bar magnet is going away. When it goes away, the galvanometer shows deflection. But you know, when the north pole was approaching, when the north pole was approaching the right side of the solenoid, the galvanometer shows deflection towards right. But now, when we are withdrawing the north pole of this bar magnet from the right side of the solenoid, the galvanometer is showing deflection. But now the deflection is in the opposite direction. Now the deflection is towards left. The deflection of the galvanometer shows that the current is induced, but the deflection of the galvanometer in the opposite direction to the previous case shows that this time the current which is induced, the EMF which is induced, has opposite direction. So understand this thing. When the north pole was approaching the right side of the solenoid, the current has a different direction. When the north pole of the bar magnet is withdrawing from the right side of the solenoid, the current induced has a opposite direction to that of the first case. So when this north pole and this whole bar magnet is moving towards right, it is withdrawn, it is moving away from this pole, the current is induced in this solenoid, galvanometer showing deflection towards the left. And due to this current in the solenoid, an electromagnet is formed on the solenoid. And that electromagnet will have a south pole on this right side. Why it will have a south pole here? Because it will try to oppose this motion. It will try to oppose this north pole going away. To stop this north pole going away, we need a south pole here to attract it, to stop it from going away. So that's the Lenz's law, that the current which is induced in the solenoid, its direction will be such that it will try to oppose the motion which is inducing that EMF, which is inducing that current. So I hope that you have understood. Let me go to the next slide. Okay, the next slide, it is when the north pole of the bar magnet was moved away from the solenoid, the galvanometer needle was deflected momentarily to the other side. This shows that an EMF was induced in the coil and a current flowed through the galvanometer. The induced current produced an south pole at the end of the solenoid to attract the north pole of the bar magnet moving away from it. So this is the academic language. This is from your textbook. This is the language in which your textbook writer explains that what happened in the slide which I explained you, the last slide I explained to you. Okay, so we have reached the end of this topic, and the one very important thing which you should remember is that when you have a solenoid and there is no source of electricity in it, there is no source of electric power, electric energy in it, and you connect that solenoid with a galvanometer to so that the galvanometer can show you the presence of the induced EMF, and you bring a bar magnet near it. If you will move the bar magnet, the galvanometer will show deflection. If you will stop moving the bar magnet, the galvanometer will not show deflection. From here we conclude that the EMF is only induced when the bar magnet is moving relatively to the coil. If the bar magnet becomes stationary, no EMF is induced. Galvanometer will show no deflection. In other words, we can say that when the magnetic flux passing through the solenoid, magnetic flux of that bar magnet passing through that solenoid, if that magnetic flux changes, then the EMF is induced. If the magnetic flux is passing through the solenoid, but it is not changing, then no EMF is induced. The magnitude of the induced EMF depends upon the rate of change of magnetic flux passing through the solenoid. So greater the rate of change of the magnetic flux, the greater will be the induced EMF. The direction of the induced EMF will be in such a way that it will always oppose the cause or motion which is inducing that current. So we have studied two laws, Faraday's law of electromagnetic induction, and we have studied Lenz's law. And here you can see the motion of a bar magnet, motion of a magnet relative to the solenoid is necessary for an EMF to be generated in the circuit. The magnitude of the induced EMF is described by Faraday's law. The direction of the induced EMF is such that the magnetic field created by the induced current always opposes the motion that produces it. The direction of the induced EMF is described by Lenz's law. You should remember this, take note. The EMF is induced in a conductor only when there is a change in magnetic flux. If the conductor is at rest in a constant magnetic field or moving in the same direction as the magnetic field lines are pointing, no EMF is induced. So it's important that the conductor should be cutting the magnetic lines, and the flux passing through that conductor should also be changing. Then the EMF is induced. When the flux is present there, it will not induce EMF. Flux should be changing. When the magnetic flux will be changing, then the EMF will be induced. I hope you have understood. Let's move to the next topics. Okay. So this slide is about the key ideas which we have studied till now. Electromagnetic induction is the process through which an induced EMF is produced in a conductor due to a changing magnetic field. Faraday's law of electromagnetic induction states that the magnitude of the induced EMF in a circuit is directly proportional to the rate of change of magnetic flux in the circuit. Lenz's law states that the direction of the induced EMF and hence the induced current in a closed circuit is always such that its magnetic effect opposes the motion or change producing it. The magnitude of the induced EMF can be increased by the following things. The number of turns in the solenoid, increase the number of turns in the solenoid and the induced EMF will be larger. Strength of the magnet, the permanent magnet which you are using, use stronger magnets and you will have larger amount of EMF induced. Speed at which the magnet moves with respect to the solenoid. If the speed of the bar magnet which is moving is larger, then the EMF induced will be larger in the solenoid. So let's move to the next slide. Okay, so here we have a basic diagram of an alternating current generator. You know, in our previous chapter, we have studied DC motor. And what the DC motor do? it converts the electric energy into motion, into mechanical energy. So what the DC motor energy wise do, it converts the electric energy into mechanical energy, into motion. And what the generator do, it do the opposite. It converts the mechanical energy into electric energy. So the basic design of the generator and the motor is DC motor is to some extent same, uh, but their functions are different. DC motor converts the electric energy into mechanical energy, and the AC generator converts the mechanical energy into electrical energy. DC motor uses electric energy and produces motion. In the generator, we provide the motion and the electric energy is produced or induced. So our next topic is about generators. You all must have observed generators at your homes, and what we do with the help of the generator, we are able to produce electricity. So if you this diagram is a very simple diagram of a very simple AC generator. You know, in the AC generator, we have permanent magnets. Here we have two permanent magnets, North Pole, South Pole. And we have a coil here. And this coil is on an axle. So if you want to rotate this coil with your hands, you can rotate it. You will provide the mechanical energy. You will rotate it yourself with your hand. So this coil, the blue coil, it is basically mounted on an axle, and you are providing it with the mechanical energy. So with your hands, you are rotating it, and you are rotating it in a clockwise manner. And when you and here, you know, this end of this coil is connected with this slip ring. Remember, this word is different. Don't confuse it with the split ring commutator. Don't confuse it with that. That is in the DC motor. Here we have slip rings. So this side of this coil is connected with this slip ring, and this side of the coil is connected with this slip ring. Here we have carbon brushes, or he says graphite. Graphite is carbon. So here we have carbon brushes, and by this carbon brushes we have connecting wires, and here we have a lamp. So when you rotate it, you will observe that the lamp will start glowing. It will lit. And when you will stop rotating this the coil, the lamp will go off. When you rotate this coil, the lamp switches on. It glows, which means that when you rotate this coil, the current is induced, and due to that current, or EMF is induced in that coil, and that EMF, due to that EMF, the bulb is switched off. So it's a very important use of electromagnetic induction, and we use it in the alternating current generators. And in the alternating current generators, we provide the mechanical energy. We rotate the coil with our hands. And what happens when that coil rotates inside that a bar in a magnetic field, current is induced in it. So the lamp will switch on. So what is happening here? That the generator is converting the mechanical energy into electric energy. So the basic structural components of a generator are: we have a coil, we have permanent magnets, the coil is mounted on an axle, and that axle we can rotate. By the axle we can rotate it. We have slip rings, and those there are two slip rings. Remember, there are two slip rings, and one slip ring is connected with one side of the coil, and the other slip ring is in contact with the other side of the coil, and with the slip rings we have carbon brushes, and with the carbon brushes we have connecting leads, wires, and then we have a lamp here. So very simple structure of a this AC motor, AC generator. So let's go to the next slide. Again, here you can see what happened here. We have a coil here. You see, we have a coil. Here we have a coil, and that coil is mounted on an axle. And with this axle, we have a handle, and by my hand, I can rotate that handle. And when I will rotate this handle, what will happen? This coil will also rotate. Here I have two permanent magnets, north pole, south pole. So magnetic field is from north to south. And when this coil will rotate, EMF will be induced in it. Here I have the slip rings. Remember this word, slip ring. One side of the coil is connected with this slip ring, and this side of the coil is connected with this slip ring. And here I have the carbon brushes, and here we have the leading wires which are taking the electricity out, and alternating current is induced. Alternating voltage is induced. So what you do, you rotate this coil by this handle, you provide the mechanical energy, and because this coil is rotating inside a magnetic field, it is cutting the magnetic lines, EMF is induced, the current is induced, and through these slip rings and carbon brushes, that EMF comes out, and this is the induced EMF is an alternating, is AC. So you can see this is the basic diagram. This is the basic diagram of a generator. You see, this is the basic diagram of a generator. Okay, here we go. Here in this diagram, you can see it's a basic diagram of a AC generator. Here we have here you have two permanent magnets, and this is north pole of one magnet, this is the south pole of the one magnet. And what is happening here? Here we have magnetic field. The magnetic field lines are going from north to south. So here we have horizontal magnetic field lines. They are going from north to south. I mean, they are going from left to right. And here I have a coil, and that coil is mounted on an axle, and that axle has a handle here. So from this handle, I can rotate it. So you can rotate it clockwise. If you want to rotate it anti-clockwise, no matter. It does not matter. Just rotate it. You need to rotate it. The mechanical energy you will provide. So from the handle, I can rotate the handle. And what will happen with that handle? That coil, we have a coil here, and the name of the coil is ABCD. When you will rotate this handle clockwise, this coil ABCD will also rotate clockwise. And one side of this coil is connected, this BC side of the coil is connected with this carbon brush, and this AD side of the coil is connected with this carbon brush. So sorry, we call them slip rings, and the slip rings are connected with the carbon brushes. These two, the dark colored are slip rings, and here we have carbon brushes, and with the carbon brushes we have leading wires, and here we have a lamp. So that lamp is switched off. When you will rotate it, the electricity will be generated in the generator, and the lamp will switch on. It will lit, it will glow, it will give you light. So here you have, so what happens when you start rotating it? When you start rotating the handle, what happens? The electricity is induced in this coil. This coil also rotates, and the slip ring also rotate with the coil, but the carbon brushes are stationary. So through those slip rings and carbon brushes, the electricity which is induced in the coil ABC will come out, and the bulb will lit. It will give electricity. So you see, by providing the mechanical energy, you are rotating it. That is called mechanical energy. So you provided the mechanical energy, and that coil, which is a conductor, was moving in a magnetic field, and the current was induced in it, and due to that induced EMF, this lamp is giving us light. So here, this first number, it is a rectangular coil of wire ABCD. The armature is mounted on an axle. The turning the handle, the coil rotates between the poles of two permanent magnets. As the coil rotates in the magnetic field, the change in the magnetic field creates an induced EMF and hence an induced current in the coil. The slip rings are always in contact with the carbon brushes as the axle rotates. The slip rings ensure that an induced current in the coil is transferred to the external circuit. The induced current powers the electric load connected to the external circuit, so the lamp lights up. I hope that you have understood this basic diagram. We will go into further discussion, and let's move. Okay, so this is a diagram which is showing you the position of that coil ABCD and the direction of the then and the EMF is induced in that coil when that coil rotates inside the magnetic field. And the second diagram there, this is EMF and the time graph. So here we are showing you that how the EMF is induced at different times, and for example, in the first position, in the first position here, you can see that in the first position here, the ABCD is a coil inside this magnetic field, and it's rotating in the clockwise manner. But right now, the coil is horizontal. So the two sides in which I am basically interested is the AD side and the BC side. So if this coil is rotating clockwise manner, so the AD is going upward and the BC side is going downward. When the coil is in the horizontal position, the AD side, because the coil is rotating clockwise, the AD side, for example, if this is the coil and this is the AD, so when it's rotating, AD side will be going up. And if this is the BC side, if this is rotating clockwise, the BC side will be going down. So it's a it's a conductor. AD is basically a conductor, and it is placed inside this magnetic field line. So when it moves upward, it cut the magnetic lines. When it cut the magnetic lines, EMF is induced in it. This BC side, it is also a conductor, and it is placed inside the magnetic field. The magnetic lines are there. When it moves downward, it cut the magnetic lines. When it cut the magnetic lines, EMF is induced here. And so the EMF induced, this this first position on the EMF time graph is shown here. The EMF induced will be maximum. Okay, so when the coil rotates in the clockwise manner, in this second figure you can see the coil will become vertical. When the coil will become vertical, at that moment, when the coil is vertical and you are rotating it, for instance, for one very fraction of a second, what will happen? The AD side will be moving towards right, and the BC side will be moving towards left. And on this instant, the AD will be moving parallel to the magnetic lines on that particular instant. So you see, AD, which is a conductor, will be moving when the coil will become in the vertical position, as in the second figure it shows. The AD for an instant will be moving parallel to the magnet, because the magnetic lines are going from north to south. They are traveling horizontally from north to south. They are going from left to right. So the AD side, when the coil is vertical, will be also moving parallel to those magnetic lines. If the AD will be moving parallel to the magnetic lines, it will not cut the magnetic lines. When it will not cut the magnetic lines, no EMF will be induced in it. In the same way, when the coil is vertical position, the BC side is moving towards left. With this arrow, you can see he has tried to show that. And it is moving for a moment, for a very brief moment. It will be moving horizontally. It will be moving parallel. The magnetic lines are also horizontal. So it will be moving parallel to the magnetic lines. When it will be moving parallel to the magnetic lines, it will not cut the magnetic lines. When it will not cut the magnetic lines, the EMF induced in the coil will be zero. So on this instant, the EMF graph will be on, on the zero EMF. Here in the diagram number 3, the coil is rotating clockwise. Now, again, it is vertical. But this time, the BC, oh, sorry, I was here. Yeah. So the coil was rotating clockwise. And in the third diagram, you can see the coil has again become in the horizontal position. But there is a change. Now you can see that the BC side is on the left and the AD side is on the right. Now the BC side is going upward and the AD side is going downward. The BC side is now on the left side and it is going upward, and the AD side is now on the right side and it is going downward. If you compare the motion of the BC, it is going upward. The magnetic lines are going from left to right. It is cutting the magnetic lines. Because it is cutting the magnetic lines, EMF will be induced in it. If you look at the AD side, it is going downward. It is going vertically downward. And the magnetic lines are flowing from north to south. They are horizontal. They are going from left to right. So the AD side is cutting the magnetic lines. So the EMF will be induced in that side. But another interesting thing, check this. Here in the figure 1, the AD was going upward. But here in the third figure, the AD is going downward. Here in the first figure, the BC was going downward. But in this third figure, the BC is going upward. So because the BC is now cutting the magnetic lines, the EMF will be induced in it. But in the first figure, it was cutting the magnetic lines, but it was going downward. But now it is cutting the magnetic lines, but it is coming upward. Now the EMF induced when the coil is horizontal will be maximum, but its direction will be opposite. So that's why you can see here, we have shown the EMF, but it is on the negative side of the EMF. It's below this zero EMF. So the EMF induced will have a opposite direction. Then the coil continue rotating. The coil will become again, vertical. This time the BC side is on the top and the AD side is at the bottom. In this moment, on this very moment, what will happen? For a very short time, the BC will be moving towards left, and the AD side will be moving towards left. Sorry, the BC will be moving towards right, and the AD will be moving towards left. On this moment, because the BC side is moving horizontally for a very short time, the magnetic lines are also moving from north to south. They are horizontal. So the BC is moving basically parallel to the magnetic lines. AD, which is moving towards left in the diagram number 4, it is moving to the left. For the very short time in this position, the AD side is moving parallel to the magnetic line. So the AD is not cutting the magnetic line. When you move parallel to the magnetic lines, obviously you are not cutting them. So the BC is moving towards the right, and it is not cutting the magnetic lines because it is moving parallel to the magnetic lines. Same way, the AD conductor is moving towards left. It is moving horizontally. It is moving parallel to the magnetic lines. So it is not cutting the magnetic lines. When it is not cutting the magnetic lines, no EMF is induced. That's why for this figure 4, on the EMF time graph, the EMF induced has been shown as 0. Now again, the coil is continuously rotating clockwise. This AD side is back on the left side, and the BC side is again back on the right side. The AD in this position is now moving in the upward direction. The BC is moving in the downward direction, because in this position, when the coil is horizontal again, the AD is going upward. It is moving vertically upward. It is a conductor placed in a magnetic field. The magnetic lines are going from north to south. They are going from left to right. The magnetic lines are horizontal, and your conductor AD is moving upward. It is moving perpendicular to the magnetic field line. So it will cut the magnetic field lines. So EMF will be induced. And the EMF induced will be the same as in the position 1. If you look at the BC is a conductor, is the part of a coil. BC is a conductor, and right now in the position 5, it is going downward. And it's going downward, it's moving vertically, it's moving perpendicular to the magnetic lines. The magnetic lines are going from north to south, left to right. They are horizontal. The BC conductor will cut the magnetic lines. So EMF will be induced in it. But this time the EMF will be, you see, the same as that in the first position. So it will be positive, opposite to this position, to the third position. So you see, when this coil continue to rotate, when this coil rotates, what happens? That the EMF is induced. And the EMF induced in the ABCD coil, and through the slip rings and through the carbon brushes, we can take that induced EMF out. If we draw the EMF time graph, we came to know that the EMF is positive maximum, then 0, negative maximum, then 0, again positive maximum, and then 0. You can see that the EMF which is induced, it is sometimes positive, it is 0, it's negative, it's again 0, and positive, and 0, and negative, again 0. So this happens. So you can see this wave, which is the EMF induced, its direction is changing. It's positive, then it's negative, it's positive, it's negative, it's positive, and negative. That's why we call it alternating current. So you see, in this coil, alternating current is induced. So I hope that you have understood this. Let's move to the next slide. Okay, here we have. This is a description of all the description which I have given to you. This is the academic language. When the plane of the coil is parallel to the magnetic field, the arms AD and BC cut across the magnetic field lines at the greatest rate. Since the rate of change of magnetic flux is maximum, the magnitude of the induced EMF is maximum. He's talking about this position. Okay. Okay. Now, when the plane of the coil is perpendicular to the magnetic field, the arms AD and BC do not cut across the magnetic field lines. Since the rate of change of magnetic flux is zero, the magnitude of the induced EMF is zero. And I can show you, he's talking about this second position. Okay. Here he says, the coil rotates half a cycle, it is parallel to the magnetic field again. The magnitude of the induced EMF is maximum. Note that since the arm AD and the CB are moving in direction opposite to those in step 1, the direction of the induced EMF is opposite to that in the step 1. So he's talking about, this location. Okay, and he's comparing it with this. So he's talking about this, and he's comparing it with the position A, 1. The arms AD in the fourth position, the arms AD and the BC of the coil do not cut across the magnetic field lines. The magnetic magnitude of the induced EMF is zero. Sorry, he's talking about this position when the coil is vertical. EMF induces zero. Okay. So then the fifth point is the coil has rotated one complete cycle. It is parallel to the magnetic field lines again, and hence the maximum induced EMF is produced. Okay. So he has explained all these 5 positions, and when the coil is horizontal, the EMF induced in it is maximum. And the reason is the rate of change of magnetic flux is maximum. When the coil is vertical, the EMF induced is zero. The reason is that the rate of change of magnetic flux becomes zero. In this position, the rate of change of magnetic flux is maximum because this side AD and the BC, they are moving vertically and the magnetic lines are horizontal. So the rate of change of magnetic flux becomes very high. In the vertical position of the coil, the EMF induced is zero. The reason is because when the coil is vertical position, the side AD and the BC of the coil, they move parallel to the magnetic field lines. So they do not cut them for a moment, for a very short moment. So no EMF is induced. So the EMF induced is zero. I hope that you have understood this. Okay. So how you can, if you have a generator, for example, this simple generator, and that generator is giving you alternating current. That generator is giving you alternating EMF voltage. How you can increase that? So there are 4 factors, and by using those 4 factors, you can increase the current which you get from a generator. Increase the number of turns in the coil. You know the design which we have studied in this, the coil is rotating. We have only a single coil, A, B, C, D, a single turn of the coil. If you increase the number of turns of the coil, the current will be more, and the current induced in the generator will be more, and the voltage induced will be also more. The EMF induced will be also more. The second thing you can do is use stronger magnets. The permanent magnets, North Pole, South Pole, the permanent magnets which we have used, use stronger magnets. If you will use stronger magnets, the amount of current induced will be also larger, and the EMF or the voltage induced will be also larger. The third thing you can do is increase the frequency of the rotation of the coil. With the help of the handle, you are rotating the coil. So in 1 second, how many revolutions that coil is completing, that is called frequency. So rotate it fastly, increase the rotation speed, increase the rotation frequency. If you will increase the rotation frequency, the amount of current induced will also increase. The amount of EMF induced will also increase. The voltage will be larger. But one thing will happen. Now the current induced will have a larger frequency also. In the first, try to understand, this is a very technical point. If you increase the number of turns in the coil, the new current and new EMF induced, they will have larger magnitudes. But the frequency of the alternating current produced will be same. If you use stronger magnet, the current which will be induced by the generator, the EMF which will be induced by the generator, the alternating current and alternating EMF, they will have larger magnitude. The current will have larger magnitude. The EMF will have larger magnitude, but the frequency of the current will be the same as that of the previous. The frequency will not change. But if you increase the frequency of rotation of the coil, the current induced will be larger, the voltage induced or EMF induced will be larger. The frequency of the induced current will also be larger. If you double the rotation speed of the coil, the current induced, its frequency will also become double. So it's a very important and technical point. Binding the coil around a soft iron core. We have this coil. Inside this coil, what we do, we put a soft iron core. When you put the soft iron core, the magnitude of the current will increase, the magnitude of the EMF induced will increase, but the frequency will not change. Okay, by putting the soft iron core inside the coil or winding the coil around a soft iron core, it will increase the amount of current induced in the generator, and it will increase the EMF induced in the generator, but the frequency will not change by this factor. Wind the number of turns in the coil using stronger permanent magnets, increasing the frequency of rotation of the coil, binding the coil around the soft iron core to strengthen the magnetic flux linking the coil. So these are the factors on which the EMF and the current induced in the AC generator depends. And the frequency of the induced current also depends upon these factors. One of the factors can change the frequency of the induced current. That factor is the frequency of the rotation of the coil. Okay, so let's move to the next topic. So here you can see, here we have tried to show, this diagram is showing you EMF and time graph. So it's a voltage time graph. On the x-axis, the time is represented. On the y-axis, we have the EMF shown. And here, the dotted line shows the first case. So you have a generator, and in that generator, we have certain number of turns of the coil, and it's moving on a certain speed, rotating on a certain speed, and the EMF and the current which is induced. The EMF graph is like this, dotted line. Now what you did, you doubled the number of turns of the coil. When you double the number of the turns of the coil, and all the rest of the things will remain the same. The frequency of the rotation of the coil is same. The only factor you have changed is you have doubled the number of turns of the coil. We have only studied with a single turn of the coil, but we put there thousands and thousands of turns of the coil. So what we have done, we have doubled the number of turns of the coil. So now the EMF graph with respect to time will be this red line. You can see that the amplitude of this graph has doubled. It was going to 1e, now it is going to 2e. By doubling the number of turns of the coil in the AC generator, the EMF induced will become double. If you keep all rest of the factors constant and you only double the number of turns of the coil, the voltage induced will become double. The rest of the things will remain same. I mean the time period of the current induced and the frequency of the current induced will be still the same. So you can see here this red graph shows when the turns are doubled, the amplitude of the graph has doubled, but the time period and the frequency is still the same. I hope that you have understood that by changing the number of turns, by doubling the number of turns of the coil in the generator, we can get double the voltage, double the EMF. I hope that this graph is clear to you. Okay, here we have again a EMF and time graph. And what we have done, we have a certain situation in which the coil was rotating, or the coil of the AC generator was rotating with a certain time period. So this is the one time period. Here two time periods have been shown here. With the dotted line, I have shown the first case. Now what you did, you kept all the parameters same, but now you have started rotating the coil with double the speed. You have, so if the coil was completing one cycle in 1 second, suppose if it was doing it in 1t, now the cycle will be in 1t, it will do 2 cycles. It will take two rotations in 1t. So here on the display, there was on the dotted graph, there were 2 cycles, but because now you have doubled the frequency of the rotation of the coil, what will happen? The EMF will become double. You can see with the red, I have shown that graph. So you can see the amplitude has doubled as compared to the dotted graph. When you double the frequency of rotation of the coil, the EMF induced in the AC generator, it will also become double. So that is shown here by the amplitude of this red line, this red graph. You can see. Okay. And you can see the time period of that red graph is half the time period of the previous case. The EMF graph completes one cycle in t seconds, but now in t seconds it completes in the red graph. The one wave is completed in t by 2, so the time period has become half. In t seconds there was one wave, but in t seconds the red one has 2 waves. So the frequency of the induced current is double. The time period is half. The frequency has become double. The amplitude has become double. You see, when you double the rotation frequency of the coil of the AC generator, the EMF which is induced, or the current which is induced by the generator, it will have, its magnitude will become double. The current also and the EMF also. But the time period of that induced current will become half, and the frequency of that induced current will be double. If the frequency of the current previously was 25 hertz, now it will become 50 hertz. I hope that you have understood that we are studying the factors by which we can change the EMF, the amount of current, and the frequency of the current induced in AC generator. Okay, here we have Fleming's right hand rule. And remember this, if you have your right hand, stretch your right hand, and thumb will be the force, M magnetic field, and C will be the direction of the induced current. This Fleming's right hand rule is used for generators. You know, we have also learned the Fleming's left hand rule. Take your left hand, stretch your fingers in this way, and you know, and we have said FMC. This is my left hand. FMC, force, magnetic field, and current. So we have Fleming's left hand, and we have studied Fleming's left hand. We have applied the Fleming's left hand in the DC motor. But in generators, we use Fleming's right hand rule. When the mechanical energy with the help of magnetic field, electric energy is induced, we use Fleming's right hand. For generators which convert the mechanical energy into electric energy, we use Fleming's right hand rule. Okay? So if this is my right hand, stretch the fingers of my right hand this way, and you know, thumb will be the force. This second finger will be the forefinger will be the magnetic field, and this second finger will be the induced current. FMC. So it says apply to AC generators when the direction of the magnetic field and the force are known. Fleming's right hand rule gives the direction of the induced current. For example, let me show you how we use this rule. Let's go back to that slide. Okay, so let's apply this here. The Fleming's right hand rule we will try to learn, and we will apply on this side. Okay, for example, this AD is a conductor. It is in the magnetic field and it is moving upward. The magnetic field is from north to south. Let's apply the right hand rule and see what will be the direction of the current which will be induced. Okay, so let's apply it. Okay, AD in the figure 1. This is my right hand. I'm going to apply the Fleming's right hand rule to find the direction which will be direction of the current which will be induced in the AD. So I have stretched my finger. The thumb is force in which direction in which the the conductor is moving. The AD is going upward, and you know, the magnetic field is, I have to twist my arm. Magnetic field is going towards north to south. My thumb is pointing, my second finger is pointing towards from A to D. Okay, you see how we have to twist our arms. So when the AD is going upward, the current induced will be going from A to D. Okay, let's apply the right hand rule on the BC in the figure 1. This is my right hand, you know, this is my right hand, and let's change the camera. This is my right hand, and stretch it. Okay, my thumb should be downward because the BC is going downward. Okay, the magnetic field is going. The magnetic field is going. You know, from north to south, and the direction of the current is towards me. So the current will be flowing from C to B. In this position, the current is flowing from A to D and from C to B. Remember this direction. Now consider this direction and this position of the coil. Now the BC side is going upward and the AD side is going downward. Apply the right hand rule. So this is my right hand, and okay, stretch the fingers. So the motion is upward. The magnetic field is going from north to south. So this represents the magnetic field. So I will have to twist my arm. So the thumb is pointing upward because the coil, the BC is going upward. The magnetic field is going from north to south. This finger, second finger, is current. It is showing that the current will flow from B to C. So here, the current in the BC will flow from B to C. In the first position, in the BC, the current was flowing from C to B. You see, in this position, the current in the BC conductor flows from C to B. But in this third position, when this BC is moving upward, the current is induced and the direction of the current is such it flows from B to C. Here the current flows from C to B. Here the current flows from B to C. You see the direction of the current has changed. It is moving now in opposite direction. In the first position, in the CB conductor, the current was flowing from C to B. But in the third position, the current is flowing from B to C. The direction of the current has reversed. Okay, so in this third position, let's apply the right hand grip rule. Fleming's right hand rule on the AD side. So this is your right hand. Press the fingers of your right hand. This is the motion. The AD in the third diagram is going downward. The thumb is in the direction of the motion of the conductor, so downward. The magnetic field is towards from north to south. The thumb is pointing towards me. Not thumb, I mean the second finger is pointing towards me. You know, I have to twist my arm. So because now it's moving, the second finger is pointing towards me. It means that the current will be flowing from D to A. A very interesting thing. See, in this position, when the AD conductor was moving upward, the direction of the current was from A to D. The current which was induced was flowing from A to D. But in this position, when the AD conductor is going downward, the current which is induced is flowing from, the current was flowing from A to D in the position 1. Here the current will be flowing from D to A towards me. In the position 1, when the AD was moving upward, the current was flowing from A to D. In this third position, the AD was going downward and the current induced, the current was flowing from D to A. You see, here the direction of the current and here the direction of the current, they are opposite to each other. So if this is a positive current, then this will be a negative current. If the EMF induced here is positive, the EMF induced here will be taken as negative. So when the AD is going upward, the induced EMF, if you take it as positive, when the AD will be going downward in the magnetic field, then the EMF induced will be taken as negative. So this is how you apply the Fleming's right hand rule on the generator. So you see, by applying the Fleming's right hand rule, I am able to tell what is the direction of the current which is induced. But remember one thing, that the Fleming's right hand rule is used for generators. Okay, remember this thing. It is not used for DC motors. Okay. So here we have, to remind you, we have also have the Fleming's left hand rule, in which we use our left hand, which strikes our fingers, the FMC, FMC force, and this is the magnetic field, and this is the current. Okay, the Fleming's left hand rule is applied on the DC motors. You use the Fleming's right hand rule when you generate electricity. And you use Fleming's left hand rule when you use electricity. When you convert the mechanical energy into electrical energy to find the direction of the current, you use the Fleming's right hand rule. When you convert the electric energy into mechanical energy and you use electric current and magnetic field to produce motion, to find the direction of that motion, we use Fleming's left hand rule. Okay, so Fleming's right hand rule, Fleming's left hand rule. Fleming's right hand rule is for the AC generator, and the Fleming's left hand rule is for the DC motor. I hope that you have understood. Okay, another very important thing is that the design which we have studied, you know, the generator which we studied, in that generator, we have fixed permanent magnets, and around those magnets, we have the magnets were stationary, and we have a coil, and that coil was on an axle. So the coil was rotating, and the magnets were stationary. So the coil was rotating. And we have to, when the coil is rotating, it becomes difficult because you have to use the slip rings, because the coil is rotating. So the current which is induced in it, you have to use slip rings, you have to use carbon brushes to take that current out and use it. But in some generators, what we do, we keep the coil stationary and we rotate the permanent magnets. You see the design till now which we have studied, in that the magnets were stationary and the coil was rotating. But the design which we will study now, in this the coil is stationary, but the magnets are moving. So the current will be induced in this coil, and we will take that current out, and it has less problems, because the coil is stationary and it's very easy to take out the connection from it. One very good example of that small generator, AC generator, is dynamo. You must have seen dynamo on, dynamo is a small generator which is connected with the bicycles. You might have seen bicycles with headlights, and they don't have any kind of battery. They have a dynamo, and that dynamo is attached with the wheel. And whenever you touch the dynamo with the, the wheel, and with the wheel, that dynamo also starts rotating. And that dynamo, we have actually permanent magnets, and that those permanent magnets, they start rotating. And we have a fixed coil, and the magnets are rotating because of the changing magnetic flux. EMF is induced in that coil, and by that we switch on the headlight of the bicycle. You might have seen that dynamos on the bicycle. So here we have a diagram of a dynamo, and you can see if this wheel is, you connect it with the wheel of your bicycle. When the wheel of the bicycle will rotate, this wheel will also rotate, and this will rotate this axle, and this axle will rotate these magnets. And when these magnets will start rotating, here we have a coil on a soft iron core. This soft iron core and this coil are stationary. They are not moving. So due to the changing magnetic flux of this rotating magnet, what will happen? EMF will be induced in this coil, and that EMF and that current will be alternating current, and that can be used to switch on the headlight of your bicycle. Okay, so a magnet is attached to an axle and a wheel. As the wheel rotates, the magnet rotates too. The magnetic field rotates with respect to a fixed coil. This coil is fixed, it's not rotating. The magnets are rotating now. This changes the magnetic flux in the coil. An induced EMF is generated, and this in turn creates an induced current. The induced current is channeled directly to the external circuit through the output terminals. Slip rings and carbon brushes are not needed. See, this design is called fixed coil AC generator. Fixed coil AC generator means that the coil will be not rotating, the coil will remain stationary, but the generators will, the magnets will rotate. And you know that in the start of this chapter, we learned that the current which is induced in the coil, that is due to the relative motion of the magnets with the with respect to the coil. So you can rotate the coil or you can rotate the magnets. One of them should be rotated. Then the current will be induced in the coil. So in this design of the generators, the coil is fixed and the magnets are moving. I hope that you have understood it. So uh, in practical applications, a fixed coil AC generator is favored for the following reasons. There are some reasons, and you know, the coil could be fixed and the magnets can be moving, or the magnets can be stationary and the coil can be moving. So, but the fixed coil design is better. Why? Why it's better? It does not require carbon brushes which wear out easily and need to be replaced frequently. That's the one reason. It is less likely to break down from overheating. This is because it does not use slip rings and carbon brushes. An eroded connection between slip rings and carbon brushes has increased resistance, which can generate large quantities of heat. It is more compact. Okay, so magnet moves, so it's more compact. I hope that you understand that the fixed coil generators, we favor them, and these are the three reasons why we favor them. Here, this is a diagram. In this diagram, we have here we have this coil. It's a big, it's a very big generator. Here we have this coil, and this coil is fixed coil. It do not rotate. And around this, we have magnets. So these magnets rotate. It's a design of a fixed coil generator. So around it, the magnets will rotate, and in these coils, the electricity will be generated. It's a fixed coil generator. So in Singapore, because your textbook is published in Singapore, it's written in Singapore. So they are talking about Singapore. Okay. Power stations in Singapore are located as Senoko, Tuas, and Jurong Island. Electricity using fixed coil AC generators. Now you understand fixed coil, what fixed coil means. That the coil is fixed, the magnets are moving around it. Several magnets, that is a rotor, rotate around several fixed coils. They are wound around iron cores, a starter. This rotation generates induced EMF and current in the starter. The induced current is fed into electric cables. How are the rotators in the AC generator rotated? They are connected to turbines, which are driven by energy sources. And for rotating those magnets around, you can either rotate it by your hands, you can rotate it by the wheel of your bicycle, you can rotate it by by a petrol engine, or you can rotate it by by on the hydrogen. So there could be different methods by which you can rotate those magnets around that coil. So here we have electric guitar, and we will try to learn that how the electric guitar works. In these are called picks. These are called picks, and on those picks we have strings. And so what happens when you touch the strings of the guitar? So that string moves left to right, left to right. It may move a little bit upward and downward also, but it will be moving left to right. But it will vibrate. What is under this pick? Let me move to the next thing. Uh, you know, and let me, before we read this, let me show you here. Here you can see, uh, this is the string of the guitar. You know, this is the string of that guitar. And here, under that guitar, this is that pick. And this pick has basically a permanent magnet in it. And on that permanent magnet, we have a soft iron core, and on that we have a coil. And you know, due to this magnet, this string will also be magnetized. When you touch this string, so now this string is also a magnet. What will happen? This string will vibrate. So this string is also magnetized, and it is moving near this coil, this blue coil, because it's like a magnet and it is moving near this coil. So this coil is inside the magnetic field of this string, and this string is moving. So due to the changing magnetic flux which will be passing through this coil, because this string is a magnet and it is moving, it has been magnetized, and that string is vibrating. So it's like a magnet moving near this coil. And when this magnet will move, the magnetic flux of this magnet passing through this coil will be changing. And due to that, the EMF will be induced in this coil. And due to that EMF, the current will be induced here, and that current is fed to an amplifier. And that amplifier is then that increase the amount of current, and by the speakers the loud sound is given out. So by the motion of those strings, by the vibration of those strings, current is induced in this coil, and that current is used as a signal and is fed to the amplifier, and that the amplifier increases the amount of current, and it feed it to the speaker, and the speaker gives out the sound. Okay. Due to the permanent magnet in the electric pickup, the steel guitar strings become an induced magnet. So these are the strings. These strings are of steel. So they also become magnetized due to this permanent magnet. When the string is plucked, it vibrates. This changes the magnetic flux linking the coil. The changing magnetic flux generates an induced EMF. The induced EMF creates an induced current in the coil. The induced current is fed to the amplifier. So I hope you have understood this. Let me go back to the slide before it. So here we go. How does an electric guitar work? And unlike the acoustic guitar, the electric guitar has no hollow body to amplify the sound made by the vibrating guitar strings. Instead, it has electric pickups which sense the vibration in the strings. These electric pickups convert the vibration into electrical signals. These signals are then sent to amplifiers and speakers, which in turn convert the signals to sound. So how do electric pickup works? Electric pickup use electromagnetic induction. A pickup consists of permanent magnets placed inside coil of fine wire. It is placed under the steel strings of the electric guitar. So I have already explained to you this diagram. So this is the pickup. Here is the steel string. In the pickup we have a permanent magnet, and on that we have a coil, and due to the presence of this magnet, due to magnetic induction, this string will also become, steel string will also become magnetized. And when you pluck it, when you touch it, the string vibrates. So it's like a magnet vibrating, it's moving. So because this magnet is moving, this string, which is a magnet, is moving, and its magnetic flux passing through this coil will change, and due to changing magnetic flux through this coil, the EMF will be induced, a small current will be induced, which will be used as a signal. It will be fed to an amplifier, which will increase the amount of the current of that signal, and it will feed it to a loudspeaker, and the loudspeaker will produce a loud sound. So this is how the electric guitar works. So by varying the size, shape, and strength of the permanent magnets, you can change the sound of the electric guitar. Number of turns in the coil, you know, the blue coil which we use, if you increase the number of the turns of the coil, and you see the sound will become loud. Position of the pickups on the guitar body, distance between the pickups and the guitar string. We can design electric guitars that produce sounds of different quality. You know how the different quality sounds we can. These are the factors on which the loudness and the quality of the sound of the electric guitar depends. So the key ideas of the concepts which we have studied in this up till now. An AC generator is a device that uses electromagnetic induction to convert mechanical energy into electric energy. So remember this, the generator converts the mechanical energy into electric energy. The slip rings in an AC generator ensure that the current generated is transferred to an external circuit. That's the function of the slip rings. The induced EMF produced by an alternating current generator increases when these are the factors. The number of turns of the coil is increased. The frequency of the rotation is increased. The strength of the magnetic field is increased. A soft iron core is placed in the coil. So these are the factors. They come in the paper. They ask you. They come in. The factors can be asked in an MCQ paper. These factors can be asked in a theory paper also. So these are the key ideas till now. And after this, the next slide, we will be going to study the Faraday's iron ring experiment.